What's up, guys? Welcome to this R session. So for today's session, we will be covering fitting neural networks with regularization under the h2o package. Indeed, that's one of the things that the neural net package, which we covered in the previous lab session, is notable for, is for its lack of regularization, which is a bit strange in the world of machine learning because obviously we need complexity controls, and the complexity controls for neural networks is regularization. Okay, and that's why we're moving on to this package. Now, as regards documentation, there's quite a bit of documentation available online for this package. It's a big package. It's a very popular package. As you will see from our lecture, there's lots of parameters you can set for any one function. It's a bit messy. So what I would suggest rather is go through this lecture where I do sort of cover all of the important bits for what we'll be using from the package. And then if you do get stuck, then refer back to the documentation. I'll try and link to everything that I think is important. And then finally, if you just want to get back up to scratch with the data set that we'll be covering today, we will be covering the Titanic data set again. So you can revisit the lab session where we covered it using tree-based models if you want to get back up to scratch. Okay, so that's that. Let's jump in. Right, guys, so for today's example, we're going to be revisiting the Titanic data. Our overarching goal here is to fit a neural network using the h2o library. We're going to be applying regularization to note the effect of regularization on response curves for such models. And then we're going to be measuring the training and validation error for a given specification. Okay, so this is sort of the things that I would expect you to be able to do in an assignment or a test or an exam. Okay, I've broken it up into a bunch of tasks again. Today there's going to be 4 tasks, so it might end up being a long one, but fortunately it's not a difficult one because there's just a lot of repetition. But in any case, let's get cracking. So task 1 says pre-process the data, create training and validation frames using an 80-20 split of the data. Use only the P class, sex, and age variables. Okay, so I'm simplifying the data set. We're only going to be using those 3 predictors. Okay. So first thing we need to do is call in the rpart and rpart.plot libraries. That's because that's where the data lives. And then obviously the h2o library, which contains all the machinery we need to do the analysis. Okay, so let's run that bit of the code. Okay, and then the first thing we're going to need to do is to initialize a so-called h2o cluster. Okay, and the way you do that is just to call h2o dot init. Okay, so what that does is that creates a local cluster on your machine. Okay, it gives you some idea of how much computing power you have and so on. And I guess this is what's nice about this this package in particular, is it allows you some scope for actually distributing your computing and speeding things up and so on. Okay, but there is a bit of a caveat to that, and I'll come back to that later as we do the analysis, because there's a bit of a price to pay for that distribution. But in any case, it's one of the positives of the package. You can do that if you so wish. Okay, but in either case, you still need to initialize an h2o cluster because all the computations using h2o are done on your so-called cluster. Okay, cool. So let's start with the analysis. First, create a data frame, split the data, and cast the training and validation frames as h2o objects. Okay, the reason we need to do that is because h2o, again, as I've just said, does all its computations on the cluster. You need to pull in the data onto that cluster. The way you do that is via these class objects called h2o objects, I guess. Okay, so first thing we need to do, create a data frame, call in the Titanic data. First thing I'm going to do is I'm going to remove the NAs, or the missing observations from that data set. So the data is in the p-Titanic data set, obviously when we call in rpart.plot. I'm going to use the na.omit function to remove any rows on this data frame which have any missing observations or NAs. Okay, and that's just going to give a data frame back of smaller dimension. Okay, so to show you what that looks like, let's go dum p-Titanic, and you'll see there's 1,309 observations on 6 variables. Now we're going to go NA omit, and then let's look at dim.dat. Okay, and then you'll see it's smaller dimension. So there's quite a number of observations with NAs. Okay. Actually, this attach needs to happen after that. Yeah, okay, so we're going to create a new data frame now. Okay, so data.frame based on this reduced data. Okay, so I'm just going to reassign this dat a bunch of variables because we're going to focus on the, obviously we want to predict survival, but we're going to focus on the passenger class, sex, and age variables only. And we need to cast them appropriately as well. Okay, so first thing we're going to do is we're going to go create survived is equal as dot factor. So just making sure it is going dat dollar survived. Okay, and then it's going to go again p class. We're also going to do that way. Is just going to be as dot factor. Not character factor. And then you're going to go dat dollar p class. Okay, and then the next one is just going to be sex equals as dot factor again. Dat dollar sex. And then the final one is just going to be age, which is just going to be dat dollar age. There you go. Cool. And that's going to be our new data frame. And when we're going to attach that so that if we want to call any of these variables in the workspace, we can do that. Okay, so let's go dat. Let's go attach. Okay, and it calls them in. Okay, you'll see I've called them in a bunch of times already. And let's just have a look at the dimensions. Let's go, okay, how many observations do we have? So let's go dimensions of that data frame. The first dimension is going to tell us how many observations there are. Okay, let's just go in. And we're going to need that if we want to split our data into training and validation frames. Okay, so let me just clear the workspace quick. Okay, and what we're now going to do, so we've cleaned our data. We're now going to do the validation split. Okay, and the way we're going to do that is by taking a sequence running from 1 to however many observations we have, and we're randomly going to select 80% of those indices as being the indices for the observations of our training set, and then the remaining ones as for our as our validation set. Okay, so the way we're going to create that is we're going to sample at random from a sequence running from 1 to n. Okay, how many are we going to sample? Well, I'm just going to go floor. You could go round or even ceiling. 0.8 times n, whatever that is, so that we just get an integer out, and then we want to sample without replacement. Okay, so go replace equals false. Okay, so what does that look like? Well, it's a set of indices, random indices in this set running from 1 to n. Okay, so let's clear that. And now we're actually going to assign our training and validation sets, and we're also going to cast them as h2o objects. Okay, so the way we're going to do that is we're going to set up our training. We're going to go as dot h2o. Okay, we're going to give it from that data frame, go on all the row indices, which correspond to those in the set that we've just sampled. Okay, and that's going to create our training set. Okay, then same thing for our validation set, only our validation set is everything which is not in the set. So go at your original data frame and take everything out which was in that set, and that will give you the validation frame. Okay, cool. Yeah, and then just so we all get the same results, what I'm going to do is before I call this sample function, I'm going to go set.seed 2021. That's going to set the seed for the random number generator so that we all get the same set. Okay, so yeah, and then I've already pre-populated this head, dat train, head, dat val. What this is going to do is just going to show us the heads of those frames. Okay, so let's rerun the analysis there. And then what do you see? Yes, indeed, it created these training frames. So you'll see this little progress bar as it transforms it from a normal data frame to an h2o object. Let's look at head. So yes, we've got our survived, which is the thing we want to predict. Passenger class, sex, and age. And age is measured in years here. So again, this is the only variable on a continuous scale. Okay, and then we can have a quick look at the dimensions of those. So let's look at the dimensions of the training data. Okay, so we'll see that, okay, it's going to be smaller than our original data set. That makes sense. We've split it 80-20. Okay, and then we also have dat val, which should be whatever remains. Okay, so we've got 210 observations in that. Okay, cool. Let's comment that out. That's it for task 1. Our pre-processing is done. What we now need to do is we want to fit a neural network. Okay, so let's go to task 2. Task 2 says fit a 5-3 network to the data using h2o.deeplearning. So this is the function you use to fit neural networks. Pick an appropriate activation or pick appropriate activation and objective functions. Set the L2 regularization to be 0 initially. Set the learning rate, so that's for our gradient descent algorithm, to be 0.001. And train for 1000 epochs. That's going to relate to the number of iterations that the algorithm is going to run. And then report the training and validation error. Okay, cool. So let's get to doing that. So we want to call the function h2o.deeplearning. Okay, and then we're going to pass a bunch of parameters to it. So maybe we want to look at the help file for that. So let's go copy that. Go question mark h2o.deeplearning, and let's look at the help file. And indeed, what do we see? Okay, now the help file for this package is a bit all over the show. It's a bit of a mess because there's so many parameters and some of the documentation is a bit dubious. But what I'm going to do is I'm going to walk you through the important ones for what we're going to do. In general, I'll actually tell you, for the most part, which things to set. You just need to familiarize yourself with these parameters. Okay, so let's look at h2o.deeplearning. So this builds a feed-forward multi-layer artificial neural network on an h2o frame. Okay, so again, this is going to run on a cluster. Okay, so we've got a bunch of parameters. Let's look at the most important ones. So I'm going to start with x. So x is optional. This is a vector containing the names or indices of the predictive variables to use in building the model. If x is missing, everything except y is used. Y, the name of the column index of the response variable in the data. Okay, response must either be numeric or categorical variable. If the response is numeric, then a regression model is fitted. Otherwise, it will train a classification model. Okay, that much makes sense. And then we need to pass a training frame and a validation frame. Okay, so these are the frames that we've actually constructed. Now, this is sort of it just says ID of the training frame. But actually what's happening here is we're passing the data using the training frame and validation frames. Okay, and the training data is what it's going to use to actually estimate the parameters. X and Y here give the indices on this training frame corresponding to the predictors and the response. Okay, so in this context, if you look at sort of our data frames here, so let's look at the head of the training data. The index for the response is going to be 1 because that's the first column. The index for the predictors is going to be 2, 3, and 4. Okay, so what we do is we specify X as being a sequence running from 2 to 3, Y as being 1. Okay, cool. Then we're going to say training.frame or training underscore frame. Well, that's just going to be dat underscore train. And remember, this dat underscore train, it must be an object of type h2o. So that's why we're casting it as an h2o object. Validation.frame or underscore frame, that's just going to be dat underscore val. Okay, so that passes our data to the function. Let's go on from there. Yeah, I guess a last bit of pre-processing that we didn't discuss here was standardization. Yes, okay. So you'll note that one of the parameters you can pass here is called standardize. It's logical. If enabled, automatically standardize the data. If disabled, the user must provide properly scaled input data. So you'll remember from our previous example that we scale the data manually. Fortunately here for this package, we can allow the package to do it. And it defaults to true, but I'm just going to include it here because that's sort of part of calling in the data, I guess. So let's go true. Right, so that's passing the data. What did our task say? We need to fit a 5-3 network to the data, pick an appropriate activation objective functions. Okay, so let's think about that for a sec. Okay, so we need to specify our neural network. Part of that is giving the dimensions, and giving the dimensions means giving it the hidden number of nodes on each hidden layer. Okay, so we're going to go hidden equals 5-3. So first hidden layer's got 5 nodes, second hidden layer's got 3. The 0th layer is obviously just the input data. That's out of your hands. The output layer is also determined by the response. That's also fixed. Okay, so those are the dimensions. Next, we need to specify activation functions. Okay, so we've got hidden there. That's just hidden layers. Activation function. What options do we have for activation function? Okay, so for activation, we've got must be one of tan h with dropout, rectify with dropout, max out with dropout. Okay, so lots of options there. The one we're going to be choosing is tan h. Okay, so activation is going to be tan h. Okay, now fortunately for this package, it doesn't suffer from the same issue that neural net did, where you specify the activation function and some of that applies to the output layer as well. Here this will apply to the hidden layers, and then based on your specification of the so-called distribution, we'll get to that in a sec, it'll pick the appropriate activation function on the output layer. Okay, so that's a great thing. That's taken care of. We'll be picking the tan h activations on our hidden layers. Okay, so that's our activation functions. Next, we need to pick an objective function. Okay, so like I said, there is this other parameter which we need to check out, which is important, and because it relates to picking the objective function. And so for this package, we need to specify a so-called distribution. Let's maybe see where it is here. Did show it there. There you go, distribution. So distribution must be one of auto, Bernoulli, multinomial, Gaussian, Poisson, Gamma, Tweedy, Laplace, blah, blah. Okay, so what's cool about that is depending on what problem you're working on, right, your response variable will determine, what things on the output layer looks like and its interface with the objective function and necessarily the objective function. So here we're going to say, for this is a binary classification problem, the appropriate distribution for such observations will be Bernoulli, right? So the distribution we pick is Bernoulli. If we have a multi-class classification problem, we pick multinomial. If we have a regression problem, we pick Gaussian. If we have a count problem, so we're modeling counts, we use Poisson and so on. Okay, so that's pretty neat because you can model lots of different kinds of problems. Okay, so we're going to tell it use Bernoulli distribution. So that's going to tell it, well, what do the outputs need to look like? They need to match with the Bernoulli distribution. And then we obviously need to specify an appropriate objective function. And in this case, that means specifying a so-called loss, or the loss parameter. So where is the loss parameter? So this is again why this is a bit difficult to navigate. There you go, loss. Okay, so loss function must be one of automatic, so I guess it specifies it automatically, cross entropy, quadratic, Huber, absolute, quantile, and defaults to automatic. We're going to tell it cross entry. Why? Because we're working with a classification problem. Okay. Cool. So that specifies everything relating to activation and objective functions. Next, we need to set the h2o regularization to be 0 initially. Okay, so let's look at the regularization parameters. Fortunately, this package, this is one of the benefits of this particular package, is it allows you to perform regularization, which is something that neural net didn't allow us to do. Okay, and why one would have or try and fit a neural network without regularization, or any machine learning algorithm without regularization for that matter, it's a bit beyond me, but in any case, that's why we moved on to this type of package, because it allows us to do regularization. And specifically, I've told you here to set the h2o regularization to be 0 initially. Okay, so it's not going to do anything now. Just for now, we'll change up the parameters shortly. So h2o regularization, and then they obviously can improve stability and improve generalization, causes many weights to be small, defaults to 0. Okay, so the default is 0, that's fine. Then next thing we need to set the learning rate to 0.001 and train for 1000 epochs. Okay, so now we're moving on to the gradient descent algorithm and setting the parameters for our learning algorithm. Cool. So that means looking for the rate parameter. Okay, so rate here is a learning rate. So higher is less stable, lower means slower convergence, defaults to 0.005. We're going to set it to be rate equals 0.001. Okay, and then we need to note one other thing. If we set the rate, the algorithm or h2o .deep learning uses an adaptive rate, so it will actually change the learning rate as the algorithm runs. We're actually, and it defaults to true in that setting, or the setting for that defaults to true, which means it always applies that unless you specify that it shouldn't. And that's what we're going to do. We're going to change that by way of the adaptive underscore rate, setting that to false so it doesn't use an adaptive learning rate. So what that means is it's going to be using bog standard gradient descent. Okay, so the step size in our learning algorithm will always be 0.001 multiplied by the gradients. Then we're going to train for epochs. How many epochs? 1000, I said. Okay, so if you're not familiar with this terminology, epochs just relates to the number of iterations in our algorithm, because at each step of our learning algorithm, if it uses only a fraction of the data, so-called batch of the data, say 10 data points out of 100, at each update, it's only going to be use 10 of those. So this sort of thing evolved where people started talking, instead of talking in terms of actual iterations of your updating algorithm, they measured things in terms of passes through your data. So if you have like a batch size of 10, 100 data points, that means you need 10 updates to get through the data once. Okay, so it's a bit of a silly way to communicate in sort of a general small problem context. But what I want you to see when you see the word epochs is really iterations, and more equals better, because generally the longer you run, the more likely it is for your algorithm to converge. In this problem, I've told you to use 1000 epochs, so we're going to set it to that. Okay, and then the final two parameters we're going to set for our h2o model finally is going to be reproducible, which we're going to set to true, and then we're going to set a seed. Okay, now before we do that, I need to explain why. And this comes back to the cluster thing we said earlier. Okay. Now, yes, everything in h2o runs on your local cluster, and the benefit of that is that you get to utilize all the power on your machine, where in general R just typically runs single-threaded and so on. And you can even distribute across a network and so on. However, there's a problem with that in that the algorithm it uses, so-called hog-wild algorithm, which sounds very interesting. I'll try and link to the paper. And it distributes in such a way that the analysis over different runs of your algorithm is not actually reproducible. And you'll see, that's one of the problems I have with this package, is that it's not quite reliable in that if you want to do things that way, your analysis is really actually reproducible. It's a bit of a frustrating thing. And it is a bit strange that one would sacrifice reproducibility for speed in the world of science. But in any case, it is cool. You can do it, and it does speed up things. So I'm sure there is a context in which that could be well motivated. But that's not this context. So what we're going to do is we want our stuff to be reproducible. And Stack Overflow tells me that in order to get our things to be reproducible, we need to actually set reproducible equals true. Okay, so now our things are going to be slower, apparently, but then we can set a seed once we do that. And for today's analysis, we're going to set a seed to 2. So what's that going to do? It's going to always set the initial parameters for your algorithm to the same set of values. You're always going to get the same answer out, supposedly, hopefully. And then, yeah, hopefully when you do this back home, you also get the same answers. And it will be reproducible across runs, which is good for us. Okay, so bit of excitement there about things running fast. Unfortunately, if we want our stuff to be reproducible, that's not going to happen. Okay, so that's everything we pass to our model. Let's see and hope that it runs. Okay, so we had everything up to there. Okay, and indeed what it'll do is it'll give you a sort of progress bar telling you how long it runs. So if you set epochs to some large value, it might run for a while. And then what you can do is, obviously it's now fitted. Everything is stored in this model object. Sorry, that shouldn't have been 2 to 3. That should have been 2 to 4. What am I doing? Anyway, it's 2, 3, and 4. Anyway, cool. So everything is on the model object. Okay. So if you just call the model object, it'll return a bunch of metrics and things that you can look at. So model details, it gives you the frame on which it evaluates some of the things, and here you can sort of see some of the structure of the model. You get your inputs there. You've got your 2 layers on which both are tanh activations. You can see that it created a softmax function to apply to the output layer. There are 2 units on that output layer. So I guess it one-hot encoded them. You can see that the L1 regularization we applied and where we applied it in the network, everywhere it's 0. Cool. So that's relating to the structure of the network. It also gives you some metrics. So why it gives MSE and RMSE for the classification problem, strange. But anyway, the thing that we're interested in is going to be log loss. Maybe area under curve. These kinds of things are useful. It gives you a confusion matrix, which is nice. So you can get some idea of its accuracy, and the rest you can read up on. And then it'll also give it for I guess this is the validation frame. Yes. So that's the performance on the validation frame. Okay. Right, so we've set everything up, we've run it. The one thing we still left to do is report the training and validation error. Okay, so the way we're going to do that is we're going to create a variable called report, and we're going to go evaluate h2o dot log loss. Okay, on our model. Okay, and then we're going to tell it to report the training and validation errors. So we're going to go train equals true and valid equals true. And what that will do is that'll report the error metrics for log loss under this particular model for the training and validation frame that you passed to it. Okay, and there you get actual values out. Okay, cool. So for this specification of the model with L2 regularization set to naught, this is our training and validation error based on the particular objective that we chose. Okay, so that's that for task 2. Let's move on to task 3. Task 3 says create response curves over age for first, second, and third class males. Note the effects for increasing L2, so the regularization parameter. So we're going to keep everything else fixed. We're going to rerun the analysis every time, increasing L2 as we go. Okay, so let's just think for a second about creating these response curves. It says create response curves over age. So remember, age was measured on a continuous scale for first, second, and third class males. Okay, so those are factor variables, and we're only asking about males. Okay, so for the factor variables in our model, so let's just have a look at the data again, in our training data. So what we want to do is we want to create a data matrix. Okay, so this is for, in order to create a response curve, we want to create a data matrix where we have one set of values over the observed range, I guess, for age. We can just set that interval. I think it's going to be 0 to 80. That's typically that's basically the observed range we had here. We're going to create regularly spaced coordinates along that dimension, and then we're going to fix along the factor variables to get the response curve. Okay, so if you think about this, first we need to create response curves over age, okay, for first, second, and third class males. So we're always going to fix sex to be male, and then we're going to change passenger class to be first, second, and third class. Okay, and then the age range will always be the same for all three of those. Okay, so first we create an age sequence. Okay, and yeah, I guess let's do it over the observed range. So let's go dat age. So starting at the minimum age range, go to the max, dat $age, and we want to create a sequence of length, I don't know, 100. Okay, then we're going to create our first data matrix, which is going to correspond to first class males. Okay, so what we need to do is create a data frame. We're going to call it xnew1. So xnew1 is a data.frame where we set p class to first. We're going to set age to whatever this age sequence is, this dummy age sequence. And then we're going to fix sex to be male. Okay, let's just check if that makes sense. So let's go, no, age sequence not found because I haven't run it yet. So let's look at the head of xnew1. Okay, does that make sense? Yes, we've got a variable called p class. First, it's always going to be first. Age is going to run from the minimum observed age range to the maximum, and then we fixed sex to be male. Okay, maybe we should just move those around so that they're the same. Let's do that. Passenger class, sex, and age. Yeah, let's do them in the same order. Okay, so I'm just reassigning that. X1. Now, next, what we want to do is we want to create predictions based on the model. We'll figure the second and third class out in a sec. Okay, let's just do the construct the predictions first. Okay, so we're going to create an object called pred1, which is going to create the predictions for our sort of first set of observations, so first class males over the given age range. And we're going to go h2o.predict is the function that we need to call in order to create the response curve. So h2o.predict using our model and give it a data frame xnew1, but we need to actually cast it again as an h2o object before we can predict for it. Okay, let's see if that runs. So you'll see there'll be one progress bar for casting it and then another one for calculating the predictions. And then what we want to do is we want to plot the predictions. Now let's have a look first at what these predictions look like. So let's go pred1. So pred1 is just a matrix. It gives you a column with the actual prediction, so the response, So whether it survived or not, and then it gives you the probabilities associated with each of the outcomes. So died or survived. Okay. Now this will be an object of type h2o, so we need to sort of recast it as a data frame so that we can access those objects. So we'll go pred1 equals data.frame, and we'll go pred1. No, man. Pred1, what am I doing? Oh. As.dataframe. I'm asleep at the wheel here. Okay. Now let's look. Okay, yeah. So that's giving us a data frame, and now we can access to objects on that. The object we want to access, we're measuring things in terms of survival probability. So let's plot the survival probability. So pred1 $survived, and we're going to plot that again. Create response curves over age for first, second, and okay, so we're fixed on first, we're fixed on males, and we're measuring over the age range. So go to x_new1 $age, okay, and plot the probability for that. Let's go type equals L, and color we're going to make magenta. And what else? Oh, you're going to set the limits. Because this is a probability, we're going to set the limits to be between 0 and 1. Cool. And there you go. It plots our response curve under this model for first-class males over the entire age range. And there you can see the age range ranges from 0 to 80. Okay, so it starts out for low ages, the predicted probability is around 80%. Along the older age ranges, yeah, it drops well below 50%. Okay, cool. But now I said create response curves over age for first, second, and third class males. Okay, so what we can do now is we, in order to create those response curves, we can just fix along the passenger class variable for its different values. Okay, so let's create two new data matrices or data frames, x_new2, x_new3, and they're going to correspond. We're going to fix along passenger class to second and third class, the outcomes for that. Okay, so x_new2, x_new3. Then we need to repeat the prediction process again. So we're going to go pred2. That's just going to be the predictions for data frame 2. Same story for 3. So pred3 pass x_new3, cast it as a data frame again. And now we can extract those predicted probabilities and we can overlay them on this plot. So let's go lines. Okay, so we can add to this plot. And now we're going to go borrow this. So we'll go pred2 survived as a function of x_new2 age. It's always going to be the same because we're using the same age dummy variable, or dummy sequence, I guess. Lines, and let's make that color for second class equals light blue. Oh yeah, it hasn't run. Let me just run everything, or let me plot the third one first. Okay, so let's go lines, plot the survival probability under configuration 3 over age, and that color we're going to make lime green. Okay, now we're going to rerun this bit of the analysis. It's always going to cast and then predict, and then it's going to create the response curves. Okay, and there you go. So now you have 3 response curves. Okay, so these are the response curves over age for first, second, and third class males. Okay, so let's maybe just add a legend there so we can see what's going on. Okay, so if you're not familiar with the legend function, we can create a legend top right of our figure, tell it to be box type equals none. The colors we're going to set to be, what did we make them? We made them magenta. light blue, and lime green. Okay, and then we obviously need to set a legend, which is the actual thing we're interested in to make sense of this figure. So legend, that's just going to be first class, second class, and then third. Class. Third class. Oh, I actually need... I just gave it the legend. I didn't tell it to make lines. What I still need to tell it is to give it a line type. I can give it anyway. So let's go LTY equals 1. All the line types were of type 1. It should be equal 1. Okay, and there you go. So now we have a legend telling us which class is which. Okay, so magenta is first class, light blue second class, third class is lime green. Okay, so create the response curves over age for first, second, and third class males. Note the effects for increasing L2. Okay, cool. So earlier on, we set the L2 regularization parameter to be 0. Okay, so this is an unconstrained neural network. What we're going to do now is we're going to systematically increase the regularization parameter and see what its effect is on the response curves, which we've just drawn. Okay, so we now know what it looks like for 0. Let's try out a slightly larger value. So let's try out 0.001 and rerun the analysis up to that point. Okay, so I'm just going to rerun everything. Okay, so it's slightly modified it. Not too surprising, that's a small value of regularization, so it should probably be a little effect. Okay, so let's increase it by order of magnitude, so it's going to be 0.01, and let's rerun the analysis. Okay, so what's happening to these figures? Okay, so it's losing a bit of shape there. Let's increase it again. Let's make it 0.1. Rerun the analysis. Okay, so it's sort of straightening or flattening out or smoothing those response curves. Okay, let's make it much bigger, so 0.5, and rerun the analysis. Okay, so what's happening? It's straightening out, and at this stage, what we're doing is we're probably over-constraining the model. Okay, so let's make L2 equals like 2. See what happens. Okay, so it's sort of completely smoothed out. The gaps between the different response curves are decreasing. Why? Because as we are turning up the regularization parameter, we're constraining our model, and the more we constrain it, the less effect the actual predictors have on the response curve. So it essentially becomes sort of just the baseline prediction, which will probably be close to the baseline survival rate now, because it won't distinguish between classes and sex here, right? So those are eventually going to sort of layer on top of each other because the actual inputs have no effect. But at this stage, the model is probably over constrained. Okay, so just the summary of that. What is the effect of the regularization? Well, it smooths out the response curves, but the mechanism by which it smooths it out is by constraining the model. And it is entirely possible for you to over-constrain the model. So we need to pick an appropriate level of regularization so that we don't over-constrain our model, so that we interpret our response curves correctly. Now, generally what will happen when I ask you to apply software like this, I will typically tell you what level of regularization to use on a given problem, and then do the interpretation of the response curve, which is what we'll do today. Or I will give you a range of values for the regularization parameter to try out, and then I'm going to ask you which is the appropriate level amongst those which you have tested then. Okay? And the answer to that, based on your knowledge of our theory lecture, will then be that the appropriate level value you choose is the one which gives the lowest validation error. Okay, so now you can see why we were reporting earlier both the validation error and the training error, because this validation error will change according to the level of regularization. So as we're tuning up the level of regularization, this validation error changes, and we pick the level of validation or regularization which corresponds to the minimum validation error. Okay, so let's move on with the analysis, and this is task 4. And now we're going to set L2 to 0.01. So we're now going to regularize using the value that I tell you to. So 0.01, we're going to rerun the analysis, and then we're going to do task 4. Okay. So let's just draw the response curves for that. Okay, so these are response curves for this particular level of regularization, which I've now told you to set. Okay. Now, before we interpret this figure, what I'm going to do is I'm going to complete task 4. You'll see why, because it's very relevant for our interpretation. Okay, so task first set L2 0.01, and then, as a sanity check on the predictions, superimpose the empirical survival rates for first, second, and third class males, but using age bins of 5 years. Okay. Now, remember in the previous analysis that we did some exploratory data analysis on the Titanic data where we looked at the conditional survival rates. So remember what we said, we created a new variable. What was it called? Dat dollar. Okay, we're going to have to use dat dollar survived. Okay. And we checked whether in our observation sets, which observations correspond to survived, so using Boolean variable. Okay, so this y now is a Boolean variable, so it's just looking directly at our data. And now if we want, say, the baseline survival rate, okay, checking when this variable is equal to survived, we can just calculate the relative frequency of the one. So R will know what to do with that. Baseline survival rate's like 40%. Okay. But what we could do is we could, for example, condition. If we wanted to if we were interested maybe in the baseline survival for males, for example, what we would do is we would create a conditional, and we would say, well, in Y, look at that, look at when sex is equal to male. Okay. And the baseline survival rate for males was 20%. Okay. Further, we could distinguish between classes. So look at all those observations for which sex is male and for which class, say P class, is first. So then we'll calculate the empirical survival rate for male passengers who are first class. Okay. And then we saw it's like 35%. Okay, so not too bad, I guess, relatively speaking. Cool, but now I'm saying, as a sanity check on the prediction, superimpose the empirical survival rates for first, second, and third class males, but now using age bins of 5 years. So what I'm now actually asking you to do is not only look at male first class and male second class and male third class, I'm asking you to break them up into age bins. Okay, so we're going to take our covariate which we observed for age. We're going to set age bins, and then we're going to break up the observations in terms of those who fall in those age bins. And that's going to give us the empirical survival rates along those age bins. And now we can then overlay them onto this plot to do a sanity check. Okay, so how are we going to do that? Well, first we need some bins. Okay, so I'm going to create a sequence running from 0 to 80. And we're going to use bins of length 5 years. So we're going to create a sequence from 0 to 80 in 5 years. Wondering if that's too narrow. Let's just go for it. Okay, so what does bins look like? So bins here these are not actually bins, these are the endpoints for the bins. So this is a sequence going 0, 5, 10, and the first bin is actually 0 to 5, the second bin is 5 to 10, the third bin is 15 to 20, sorry, 10 to 15, and so on. Okay, and now what we're going to do is we're going to condition on observations falling in those bins. Okay, so in order to do that, we're going to write a loop, but first we need to create some storage. Okay, so we're going to create some storage called emp1 for empirical, and we're going to repeat some NAs, and we're going to repeat it, whatever the length of bins is, -1. Why? Because bins is the endpoint, so there will be one less than the number of endpoints bins. Okay, so emp1 is now just going to be an empty vector. And now we're going to loop for I in 1, or let's go 2 to length bins. What I want you to do is loop and calculate the empirical. So emp, and we're going to go I-1. Why are we going I-1? Because I is going to run from 2, 3 all the way onwards. We want to start indexing from 1, so I-1 is just going to be the mean of whatever the relative frequency of this response, conditional on being male, conditional on being first class, and then conditional on that $h being less than or greater than or equal to bins I-1, so the left point of that interval, okay, the ith interval, and then less than the right point of that interval, which is bins I. Okay, so it's now going to create an empirical survival rate for each of those bins. Okay, so let's run this, see if it doesn't explode. Yes, and then for the last one, it didn't calculate anything because I guess nothing fell in that bin. Okay, that's fine. So our bins maybe are too narrow. In any case, what we're going to do is we're just going to overlay that. And how we're going to overlay that is by drawing points. We're going to go emp1, and we're going to write it as a function of what. So which ages do these empirical probabilities actually correspond? Okay, so we're just going to plot them at the midpoints of the bins, right? So where do the midpoints fall? Okay, so we're going to go concatenate bins. We're going to chuck away the first element in that sequence, and then we're going to subtract half the bin width. Half the bin width is going to be 2.5. Okay, so if you're not sure what stats does, this is the endpoints for our bin. It goes 0, 5, 10, all the way up to 80. Okay, what does bins -1 do? It throws away the first one. Okay, why do we need to throw away the first one? Because this thing will be of length 1 less than bins. But also we don't want to plot at the endpoints of that interval. We want to plot at the midpoints. What are the midpoints? It's going to be -2.5. So what are the midpoints of the bins? It's going to be 2.5 for this bin, 7.5 for that bin, and so on and so forth. Okay. And then we're going to make this color is going to be magenta. Cool. And let's make it BCH 16. Solid. Okay. Cool. So those are the empirical survival rates for the first class males. Let's do the same thing now, but for second and third class. Okay, so same thing. We're just going to change things to emp2, and we're going to condition on second class. Same age range. We're going to plot emp2. The color is going to be light blue. And let's do 3 as well. Okay, let's run that and then... Okay, so those are the empirical survival rates for second class males. Okay, then for third class males, what do we see? lime green. Oh yeah, and then we need to change that. Okay, so add that. Okay, so now we've overlaid or superimposed our empirical survival rates as a sort of sanity check. Does it seem like our model predictions make sense? Well, if we look at the response curves, do they generally track the empirical survival rates? It does seem so. Something interesting that does happen is if you look at okay, so the first class ones, yes, the survival rate goes up as you go down in age. I guess here to the left, it's pulled up by the high survival rates amongst the young people. Same thing happens to second class. So even though you have a lot of, so in some of these age ranges, you have very low survival rates because you have 2 up here, it's sort of pulling it up. And then amongst the third class observations, there are no high survival rates. So yes, there it probably tracks the best. Okay, so they sort of generally track, sanity check makes sense. Now we can sort of maybe interpret what's going on. Okay, so how would we interpret these response curves? Now remember, this interpretation is predicated on our level of regularization being correct. I've told you here now to use 0.01, so if I tell you what that value is, you may assume it's correct, unless we actually do a validation analysis, in which case you have to pick the correct one and then go on. Okay, but let's now assume that this is the correct level. Okay, so let's interpret this figure. Okay, so what can you tell me? Well, based on the response curves, obviously the predicted survival rates decrease for all classes, and they decrease quite rapidly with age. The first class passengers fared much better than the second and third class passengers. Second and third class passengers, there seems to be little difference between their predicted survival rates for most of the age ranges, although it seems that for the younger individuals, second class passengers had a much higher likelihood of survival. Okay. Yeah, and I guess the important observation here is, sort of general observation, is the delta between the classes. So even though the shapes are more or less similar, sort of decreasing as age, because I guess the decreasing is less severe for the first class passengers, but the delta seems to be between first class and then second and third class, where there seems to be little difference between second and third class passengers or male passengers. Okay, so that's that for this one. I might leave an exercise or two after the video, and then I'll see you in the next one.